Welcome back. In this outing, we talk about a beautiful science which evolved through largely through the efforts of engineers and technical hands, and that is what we know as thermodynamics, wherein evolved the concept of thermal energy. Okay. It's basically dealing in what being converted into heat and vice versa. Heat being converted into water. Historically, going back in time, heat was considered as fine indivisible fluid filling pores of a substance, and this invisible fluid was given the name caloric. Caloric used to flow from cold bodies into hot bodies until caloric levels equalize, which we today know the equalization of temperature in that steady state. This concept was there. There was a gentleman, as the name suggests, Mr. Benjamin Thompson, who was later on given the name Count Rumford, a military or a title given in the British Empire. And in 1798, while he was supervising the boring of a brass cannon, and any cannon for that matter, they found that heat is generated, and the heat generated was enough to boil a certain amount of water. Now, the work used to be done by horse. Normally, it's horse power. Okay. Of course, it could have been a buffalo power or a power by oxen, bullocks, had it been conducted in India. Anyway, horsepower was a unit of power in those times. So he found that the heat which is evolved, which is generated, is a function of the work done by the horses, and it did not depend upon the sharpness of the drills. So which led them to the concept that the heat is a form of energy. So what is heat? Heat is a form of energy. And the thermodynamics, which we are dealing just now, deals with the concept of heat and temperature, and also interconversion of heat and other forms of energy. Okay. It is a macroscopic science, not microscopic, macroscopic science. Okay. The concepts and laws of thermodynamics were formulated in the 19th century. 19th century means from 1800 to 1900. Okay. Much before the molecular picture was established. Much before the discovery of electron, proton, neutron, etc. Okay. The concept of molecules and the chemistry related with that was evolved later on. Okay. So the molecular picture is the picture that we now have, and we explain thermodynamics and its principles, its experimentally determined laws which are logical okay, with the molecular concept of, okay. So thermodynamics deals with bulk systems. It's a microscopic science. What does that mean? It does not go into the molecular constitution of matter. Anyway, when the thermodynamics evolved, there was no molecular constitution of matter. Then it deals in a relatively few macroscopic variables of the system, suggested by common sense, which is not so common, okay. Like Bernard Shaw said that common sense is not common. But anyway, deals in relatively few macroscopic variables of the system suggested by common sense that can be usually measured directly. So, for example, the state of a gas can be determined by 5 measurables, okay. The pressure, the volume, the temperature, the mass and the composition. These things are measurable things, and these things are concerning the bulk of the system, that is the microscope. Now, thermodynamics, there is a part of that word is dynamics, and we have dealt in the dynamics and also the kinematics of matter, okay, in motion in several directions, etc., etc., all kinds of motion we have already dealt in mechanics, okay. So it does not concern the motion of the system as a whole, like it is of concern in the case of mechanics. Rather, it is concerned with the internal macroscopic state of the body. Internal macroscopic state of the body. Okay, and now let us talk about what is thermal equilibrium, or even we can call it the state of thermodynamic equilibrium. Okay, in the thermal equilibrium, macroscopic variables which characterize the system, pressure, volume, temperature, mass, composition, etc., in the case of gas, they do not vary with time. They are not a function of time. For example, the gas inside a closed, rigid container, completely isolated from the surroundings, with fixed values of those 5 variables, okay, is not a function of time. In that case, we say that the state of thermodynamical equilibrium or thermal equilibrium has been achieved. So, whether or not a system is in equilibrium depends on the surroundings and the nature of the wall that separates the system from surroundings. Repeat, it depends on the surroundings and the nature of the wall that separates the system from the surroundings. Now, let us take 2 gaseous systems between which there is a wall. I have not made it the way they present there, just schematics. There is a container A and there is a container B. There may be a gas of mass Ma and a gas of mass Mb. The measurables there are pressure and volume of the gas in container A and pressure and volume of the gas in container B. These are the 2 characteristics which characterize the system. Okay. And there is an insulation. There is an isolation of the whole system. For this is the surrounding, and for this one, this is the surrounding. Okay, these two systems. I'll define the adiabatic wall and then tell you that there is an adiabatic wall over here also. Adiabatic wall is an insulating wall that can be moved also. Okay? It does not allow flow of heat from system A to system B or system B to system A. Okay? Does not allow the flow of heat. Okay? So any possible pair of values, PA, VA, is in equilibrium with PB, because you stay in your home, I stay in my home. No Alex, hello, hi, this, that, anything. So no connect. So this adiabatic wall is there also, which can contain the system from the other surroundings. We are not concerned with that. So any possible pair of values, okay, in equilibrium with the other possible values of in the container. Okay, so they don't have any concern. Two families living very separately from each other, they don't know each other, no nothing. Okay. But if the adiabatic wall that is between the two containers, this is replaced by a diathermic wall which allows the flow of heat from A to B and from B to A. Hi, hello, auntie, how are you? Hello baby, how are you? Like that. So now the two families of gases, they are in connect with each other. And then what happens is that there is an exchange, there is a variation. The two families mingle with each other until the parameters of this family and this family, they are adjusted to new values, PA prime, VA prime, and PB prime, VB prime. Okay, I'm sorry. PB prime, VB prime, any values. And then we say that the two states are in equilibrium. So the equilibrium is achieved after we allow the flow of heat from this side, from B to A and A to B simultaneously, one time, to achieve new states of whatever is contained there. Now you can just imagine that there is a parameter which will evolve with this PA, VA and PB, VB going to P dash, 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 new values. Okay. And that is, we can just say that the temperature of the two sides will be the same. Look here, in the development of this concept of thermodynamics, we have mentioned that of the 5 variables, there is variable of temperature. But actually, we have to define temperature thermodynamically. And the laws of thermodynamics, the first law, the second law and others, okay, they evolved, they were accepted, they were experimentally found to be valid, and they were in practice. But then evolved another law, and that law is called the 0th law of thermodynamics. What 0th? 0th. 0th. Okay. So because the number was already given before, so 0th law of thermodynamics was evolved, and this 0th law actually gives us the concept of what is temperature, which we'll deal in details in the next outing. And thus I have been able to introduce you the thermodynamics without dealing in any of the laws of thermodynamics, which we will follow. So thermodynamics, always remember, that is a science which is not microscopic but macroscopic. It deals in what is known as the common sense, which is, again I will say, common sense is not very common, but anyway the variables that can be measured, we can say that the measurables, pressure, volume, temperature, mass, and the composition, that determines the states, and this is what determines the state of equilibrium, thermodynamic equilibrium or thermal equilibrium. Thank you very much. See you again.